2, 1.
Hi, welcome to another episode of Build with DynamoDB. My name is Ed Zolich. I'm a NoSQL specialist focusing on DynamoDB, and today we're going to talk about advanced NoSQL data modeling with Amazon DynamoDB. So we started last time with an example about modeling a movie database. So I'd like to take that example to completion this time and to really focus on the steps involved in the modeling. So this is an interesting example because, well, we can all relate to movies, and rather than go with a very simple tutorial data model from DynamoDB documentation, I extended it to include additional entities so that we have movies, movie actor and director entities. So I'm using an entity relationship diagram to show these entities as well as relationships between them. So an entity is an abstraction. It can be anything that we're modeling in our software model or database model from real life. In our case, we have movies, we have actors, and we have directors. And our access patterns really reflect these entities, right? We have an access pattern that's about finding a movie or actor or director by name, or get movie details, get actor details, and so on. Then we also have relationships in access patterns, movies and directors and actors. Find all directors that an actor has worked with. One way to think about entities is they are always represented using a noun. And relationships are represented usually using a verb. So for example, an actor has worked with a director, a movie has actors, and so on. So let's see, one other thing actually, entities can be independently identifiable, which is the case here. Movies can stand on their own. We can have a movie, an actor and a director entity on its own. By contrast, for example, we might want to have photos associated with an actor or a director. And if we decide to ever remove that record, that photo would be removed together with the actor or a director record. So that's a weak entity. That's or a child entity, right? Let's see how we model these entities. And so looking at our entity relationship diagram, and by the way, I didn't mention, the only reason I have my phone here is so that I can get notified about maybe questions that you all might have in the chat room. Today I also have my coworker on the same team. We work together, Pete Naylor. He's in the chat room answering your questions, and I'm just hoping that I'll remember to pay attention to my phone, and if you guys have interesting questions, the idea is that I can get them answered here. If not, if I forget, we always have next time. So anyway, back to entities and relationships. So the easiest place to start is to model these entities, right? And this is a stab at modeling, showing a movie, actor, and a director item in what will become our table and our data model. As you remember from one of the previous shows, we talked about modeling many-to-many relationships, right? And that takes a table and a GSI. So it also takes having a partition and sort key so that the partition and sort key are reversed between the table and the GSI. So one of the things, of course, that we need to think about is about each entity. What data does it have? What properties does it have that we want to show in a view for that entity? And the other thing we need to think about is partition key. In our case, this partition key will actually uniquely identify each entity, even though we have a sort key. Sort key is really reserved to model relationships with other entities. So in this case, we're using a unique identifier for these entities. Movies are kind of strange, right? We're kind of straying a little bit from the common, the standard best practice of using a known pattern for our primary or partition key. And that's simply because it's hard to find something that's inherent in movie data, in a movie record, that uniquely identifies it. Title itself, as you know, is not enough. If we combine title and year, we're still not really certain that that'll work. And so the foolproof, fail-safe approach is to use a unique ID in this case. And we're going to do the same for actors and directors. And the reason is, this is public information about actors and directors, right? I mean, normally in a people database, there's something else that uniquely identifies a person, entity, right? That could be an email address or something else, right? So in our case, I decided to, for these items that contain entity-specific data, I'm actually just going to repeat the partition key as the sort key as well. And that'll come in handy later. By the way, that doesn't have to be the same, right? You could choose to call this something else. It's your own convention, right? Sometimes we see this called out as metadata, right? Sort keys metadata for the entity item, or a zero record, or something like that, that we know represents that sort of entity specific item. So now that we have entities and we know what we want to show for each entity view, if it's movie, we'll show year. S name is the search name. So we'll see how we use that in a GSI if we're looking for a movie. Same for actor or director. And then we have, of course, all these other attributes that we're interested in. Next, let's look at how we model relationships between different entities. So to model a relationship, we need a sort key, right? And so relationships are identified by the combination of the partition and sort key. And of course, that's a two-way relationship. One way, one direction, movie actor, is modeled by the table in this example. The other side of that relationship, actor movie, is modeled by the GSI. So the interesting thing about that, the data that we have in this relationship record has to satisfy both views. So if we're showing a movie detail, we're likely to have actor name, character, CO is the credit order. But then you might wonder, why do I need a title again? I know that I'm in the movie detail for this title. Well, we'll need title for the other side of that relationship, for the actor movie. So if we're querying the GSI for an actor, and we want to show what movies they were in, if we don't have the title, all we have is the partition key, the ID. So then we would have to actually make an extra query to get the title. Since we want to really satisfy the whole view with a single query, single request, we will just add the title into the relationship record. So the idea here is that we can really minimize the number of round trips that we do with the database and show basically information that we need using a single query. So if that's a movie detail, that's going to be the table, and if it's the actor detail or a director detail, that's going to be the GSI. And so speaking of queries and access patterns, we should start with the most important ones. And then the question is, what are the most important access patterns, right? So in our case, movie database, I'd like to be able to find a movie that I'm looking for. So first, I need to be able to find a movie or an actor or a director. And then the point of that is so that I can see detailed information about a given movie that I'm looking for, or an actor or a director. So movie database, first pattern, find the movie, and then show the detailed information for the movie. So finding a movie, or in fact person by name, we'll introduce another global secondary index, and we'll use the field attribute sname as the partition key for this global secondary index. So when we search for a name on this index, we'll be able to get movies, actors, as well as directors using this single, basically, GSI. So we're essentially overloading this GSI to get information about all entities that we have. Now, the other thing about GSI's global secondary index is we can project attributes from the table items that we need. And in this case, we need to figure out, once we find a given movie or actor or director, what are the attributes that we should have that we can present in that view. And for movies, that could be year, simply name of the movie and the year. And in that case, the next step would be, if I'm interested in that movie, I can click on that movie, use the movie ID. I'm going to use this laser pointer, right? Use the movie ID to get to the full record about the movie. For actors, usually we'll see something like known for, movies, shows that are the best known for, and I can add that information, those attributes, into the GSI projection for actors and directors. So GSIs are very versatile, and so here we're using one GSI to query, in fact, different types of data that we have. Two, for each type of data, we can present different attributes that make sense for that type of data. And three, by not projecting the entire item, we're being more efficient, possibly cost-effective, definitely cost-effective, because the size of that GSI is not unnecessarily large. So how do we get movie details? Now that we've, let's say, searched for a given movie, Blaze, we want to see the details. We click on the link in the window, and how do we get the details for the movie? We'll query the table on the ID, right? So the record in this case should include entity detail, right, which is this top item, but also other related information. So relationships, what actors are present, were in that movie, who was the director, and so on. And the query itself, if we query just on the partition key, we're going to get all of the records that have that same partition key. So to get the full item hierarchy, as it's called, right? So all the items that share the same partition key, we just need to specify the partition key, and we have it all. Now you'll notice that the sort key contains IDs for actors and movies, and we get that whole item hierarchy in a single query. Then we might need to basically sort it in a specific order. For example, actors, we might want to sort in credit order and then display it that way. So next, if we want to get actor details by ID, we can query the GSI on that actor ID. Remember the search that we did for a movie? We use the same global secondary index to search for actors as well. So that search returns a record that will include the primary key, the partition key for the actor. Now we can get the full detail for the actor. We search the GSI. And of course, this record will include all the movies that the actor has been in. And by the way, now we see the reason why we have the title in this record. We didn't need a title for the movie detail, because we already know we're in the movie detail for this title. But when we do a query on the GSI, if we don't have the title, all we have is the movie ID, the partition key. And if we would like to show the title of the movie, then we would either need to query for the table for that partition key, or we can simply project the title into this record. So this record, again, is there to basically include both materialized views for movie actor as well as actor movie relationships. And next, if we need to get director details by ID, we would again query the GSI on the director ID, and same thing as with actor, we would get all the records from the GSI that have that same director ID as the partition key. And so that would include the entity specific record, which is potentially director's bio, date of birth, and all these other fields, maybe a photo, and then all the relationship records for the movies that director has worked on. And so that's the relationship between movies and these other entities, actors and directors. You'll notice that I actually used a different approach for this particular record, which represents actor-director relationship. I prepended it with a special prefix because I actually don't want that record to show up when I'm showing the detail for director or the actor for that matter. So we'll go into that next. If we want to find all directors that an actor has worked with and we use the actor ID, we would query the table for actor ID and get the record, basically item hierarchy that is of all the directors that have worked with that actor. And the reverse relationship is finding all actors that a director has worked with, and for that we use the director ID. So here the reason I have this hash basically is to separate that and prevent it from showing up when I'm looking for when I'm searching just for the director. So in other words, when I'm showing a director detail, I want to see basically director's bio, date of birth, and so on, and movies that director has done, but I don't want to see all the relationships with other actors in that same detail. I want that to be an extra step. So I'm using a prefix, just a convention in my access pattern and application to make that an extra step to basically show the relationships with actors that movie has worked on. Now you might wonder, what about that particular relationship? Because if I am looking for all the actors that a director has worked with, again here I don't have the actor name. I get the if I do this query, I am going to get this actor ID, but not necessarily the name. So to fix that, we will simply add actor name to this relationship item, and that way we're doing a single query to satisfy the question, to answer the question, what actors has this director worked with? Also, an actor can work with the same or director multiple times and vice versa. How do we represent that? There's more than one way to do that. Clearly, this relationship, this item, has to be uniquely identifiable between the partition and sort key, right? So one way we can do that is simply have an attribute in this record that's a collection of titles that are about collaboration between these two persons. So it could maybe be a list of titles, and each item in the list could include the movie ID, the title, and year. That way, if we're showing this relationship we can actually see all the work, all the collaborations that they've had. And in fact, not only that, another way to model this would be to say, well, okay, it's a relationship, but sometimes it makes sense to promote a relationship into a full-blown entity. So in that case, we can call this relationship a collaboration. And if we do that, that means that this new entity should have its own partition key. So we would create a partition for collaboration. And in that case, every collaboration would be a unique record, a unique item in DynamoDB. So there's just a couple of different ways that we can model these things. And it really goes back to what makes sense for a particular access pattern from performance perspective as well as cost perspective, right? We're always aware of the goals, right, of these data modeling exercises, right? We want to be able to effectively, efficiently answer questions from a database in a way that's going to scale and perform at scale, and that's going to be cost effective as well. So next, we have a version 2 of this data model. It's a kind of a change to the data model that's really based on the notion that one person, in this case Ethan Hawke, is both a director and an actor. And is there a different way to model that? And of course there is. There's always a different way to model something, and it really, again, goes back to what makes sense for your access patterns and materialized views, right? The shape of data, the velocity of data. The other question is, we haven't really talked about how do we update these things, right? And for example, in this case, if we have Ethan Hawke actor and Ethan Hawke director, we effectively have two entity records for basically the same person. So one situation that's possible as a result of that would be that if these two entities are not really kept in sync somehow, you could go to the information record about the actor Ethan Hawke and see that the bio is slightly different from the bio of Ethan Hawke, the director, right? So one way of avoiding that is to make sure that we really truly only have one single entity item for the same person, right? So we could still keep the notion of actors and directors, entities, actor and director, and maybe simply make one point to the other. That's one option, with pros and cons. Another option is to simply conflate actors and directors into a single entity that can have multiple roles. So one role is a director, another role is an actor, and then using attributes to really indicate whether a person has a particular role. So in this case, for example, we conflate entity and a director items for Ethan Hawke. We remove the relationship for the director, but we add that record to the existing relationship for Ethan Hawke to indicate that he's also a director as well. And then we still have the same pattern that we're using for actor-director relationships. And now this becomes a conflated sort of representation of that relationship where we see within this relationship that the movie role is implicit because there is a character, there is a credit order. We could make it explicit, right? Right now it's implicit. The director role is more explicit because we have a special attribute for it. But in either case, now we're in fact using just a person entity to model both actors and directors. So as we can see, there's always more than one way to do a data model, and the process is iterative, right? For example, we started in this exercise by modeling the entities, And we know that entities have to have a unique partition key. The sort key, we can decide on a convention that we want to use for the sort key. In this particular example, it really made sense to make the sort key the same as the partition key. Sometimes the other thing to be aware about the choice of sort key, because this is a many-to-many relationship, the sort key will become a primary key in a GSI. So we have to make sure that we have enough high cardinality for that sort key, right? So that we don't get back pressure for the GSI on writes or reads, right? So that sort key should be unique enough that we avoid creating a bottleneck basically on the sort key, which is in fact the partition key for the GSI. Another question now, when I go, I like movies. I wouldn't call myself a movie geek or a movie buff, but I've always been interested in movies, watching movies, looking up information about movies. So you can think about this database as maybe this is a database for movie buffs, right? Because we're showing something, maybe we're adding value to this movie database by calling out specific relationships between movies and actors, people, right, in movies. So, and of course you can take this beyond to include other relationships and so on. But typically when we search, movie databases such as IMDb, it's pretty clear that there's a text search behind that, because it's just more powerful, right? There are search capabilities in there. And how could we, as a maybe next iteration on this, how could we add full text search capabilities to our data set here, right? So with DynamoDB, we would do that using Amazon Elasticsearch, right? Amazon Elasticsearch is a search service that really creates indexes data, right, that you feed it, and then makes it searchable. It's very configurable, very powerful, and under the hood it actually uses a really powerful search technology called Lucene. And so how do we integrate DynamoDB data, our movie database, with Elasticsearch? With DynamoDB, the best way to do that is to use DynamoDB streams, which is a transaction log of all change records to your data in DynamoDB. And it's easy as enabling that on a table. If you remember the first episode, we had to enable streams for global tables in DynamoDB. Global tables use DynamoDB streams as well. And for search, we can enable DynamoDB streams, use a Lambda function that integrates really well with DynamoDB streams to get all those changes from your DynamoDB movie table, and then write them to Elasticsearch. This, of course, is an asynchronous operation, but in our case, we have a database of what's really reference data, right? Movie data that does not change frequently, but it's read very frequently. So because of that, it's perfectly acceptable to have this additional latency of propagation. The propagation is asynchronous, but it's reliable, right? DynamoDB will reliably deliver data using DynamoDB streams to consumers that want to read it. In this case, Lambda service, when we create a Lambda function, we can use our DynamoDB stream as the source to the Lambda function, and then that Lambda function will start getting events, batches of events that represent changes to your data in your DynamoDB table. The Lambda simply takes the data, feeds it to Elasticsearch, and now you have a searchable movie database. The other nice thing about this approach is it effectively enables the separation of your sort of OLTP side movie database which of course in this case, like I said, its reference data in any case does not change very frequently, but still. And then search side, we have Elasticsearch, a dedicated Elasticsearch cluster that we can size as needed, right? And so they're independently configurable, sizable services. On the one hand, our database, right, where we can control the capacity in DynamoDB however we want, and on the other hand, we have querying capabilities, search capabilities in this case, with Elasticsearch. And so this is effectively a one implementation of command query responsibility segregation, or CQRS pattern as well, that in this case uses DynamoDB streams and Lambda as a reliable delivery mechanism that we use to deliver events from DynamoDB to Elasticsearch. And that is really all the content that I had for us today. We will continue next time with another data modeling example. We'll have Rick Houlihan again, and in the meantime, please come with questions. We're happy to take your questions live and answer them. And I do see Underground Cheese Weasel question: in the current movie database context, how could we connect our DynamoDB to Redis or Memcache server? For example, I might want to pre-cache a list of movies that a user has in their collection in order to quickly display on a web page. Yeah, so for connecting with Redis or Memcache, so in this case Elasticache, there isn't a built-in integration like there is with Lambda, but in fact we can use the similar approach. For example, updates that are coming to DynamoDB can be made available to Elasticsearch the same way we're actually updating, to Elasticache, the same way we're updating Elasticsearch using DynamoDB streams and Lambda. In this case, Lambda would simply write to Elasticache, Redis, or Memcache instead of Elasticsearch. One other thing that I'd like to point out, DynamoDB has its own caching layer, DynamoDB Accelerator, or DAX, that integrates with DynamoDB seamlessly so that these updates can happen without you really having to do anything special about it. So DAX is write-through cache for DynamoDB. So if you have DAX in front of a DynamoDB table and you simply do reads and writes through DAX, then DAX will actually keep the cache of all the updates. DAX will automatically update its cache with your changes. The other nice thing about DAX, it's not a look-aside or write-aside cache. It's a write-through cache, and it uses the same API as DynamoDB. So the changes to introduce DAX into your solution are fairly minimal. The client is different, but it implements the same interface. So the only really change is to your code is to instantiate a DAX client. So a couple of more questions coming through. Okie Bears, are companies actually using DynamoDB in real prod apps? Great question. DynamoDB is used in real production apps, I believe, in over 100,000 real customers, so including Amazon, right? So in fact, one of the reasons that DynamoDB exists is because of these scalability issues way back in early years of this century, when the internet was very, very young, and Amazon needed to scale its e-commerce business. That gave rise to NoSQL. Dynamo was the first technology, and then DynamoDB is a serverless, fully managed and evolved version of the NoSQL database that we have today. Many other companies use DynamoDB in production across a variety of verticals. In fact, just recently, I've wrote 2 blog posts about design patterns in a couple of verticals, ad tech and gaming. I'm working on some other verticals that will include retail. So for example, one of the customers of DynamoDB is Nike in retail industry, where they have some really interesting scale problems around um, um, e-commerce, right? Events that they have, sale events, and they've even blogged about it. So if you go out there, there's a lot of really good content about how different customers use DynamoDB. Samsung is another interesting example. They gave a presentation about how they use DynamoDB at reInvent. Forget whether that was a couple of reInvents ago, where they talked about how they migrated to DynamoDB, and I believe the amount of data that they now have in DynamoDB is I think 100, close to a petabyte basically, and it's a backing database for the profile data for I think it was Samsung Galaxy phone for them. So DynamoDB is the database that a lot of customers use for highly well, mission critical use cases that need scale and performance at scale. So the answer yes is yes. Many companies are using DynamoDB in real production. Another question from Underground Cheese Weasel: is that an in-memory solution like Redis or Memcached? So this question is about DAX. Yes. Sorry, I did not mention that, but DAX is an in-memory solution, just like Memcache and Redis. The main difference, though, is that DAX is really specifically designed, created for DynamoDB. And of course, the benefit is that the API is the same as DynamoDB, and it's easy to integrate in your existing applications. And looks like that was it for questions today. Thank you for watching, and join us next time. We'll have Rick Houlihan, and we'll talk more about advanced NoSQL design modeling. We'll use another real-world example, and thanks again.